Welcome everyone. Thanks for joining us for today's webinar where you'll be learning about the cost impact of tolerancing spherical lenses. Before I introduce today's speaker, I'd like to go over a few housekeeping items. If you experience any technical difficulties during the presentations, please contact WebEx directly at 1-866-229-3239 or visit help.webex.com. If you have topic-related questions during the presentation, please type them into the Q&A portion of the WebEx control panel, which is currently being shown on your screen. In side-by-side mode, Q&A can be accessed via the top right corner of your screen. In full screen mode, Q&A can be accessed by hovering over the control panel at the top of the screen, selecting the down arrow at the end of the panel, and clicking Q&A from the menu. We have a team of expert engineers in the room to answer your questions in real time, and if we do not answer your questions during the presentation, we'll get back to you individually following the webinar. Please note that if you submit a question via the Q&A, both the question and the response will be private. Other attendees will not be able to see this information. Please also keep in mind that this webinar is being recorded. A link to the recording will be sent to all participants after the webinar for your convenience. Moving on to today's presentation, I'd like to introduce our presenter, EO's optical materials expert, Nathan Carlie. Nathan received his PhD in materials science and engineering from Clemson University in 2010 and has spent the last 7 years developing materials and technologies for high-powered lasers and IR optics. He joined the Edmund optics team in 2016 and serves as R&D manager at the corporate headquarters in Barrington, New Jersey. Nathan holds 6 patents and has written over 40 papers and articles on the design and fabrication of optical materials and systems. So without further ado, I'm going to turn it over to Nathan.
Thanks very much for the introduction. So today, as you heard, we'll be talking about the cost impacts of spherical lens tolerancing. We'll be going through how you optimize the cost-benefit trade-offs between the tolerances in the lenses and in the overall system. We'll look at centration, power and irregularity, surface quality, and the coupling of those specifications together into the overall system. So first, we'll start with centration. So what is centration? Well, if you were to measure the outer diameter of a lens and find the center of that curvature, and then measure the surface of the lens and find the center of that curvature, if those two centers aren't in the same place, then there's decentration of the lens. Mechanically, what that will mean is that there's a slight wedge in the lens, or it will be slightly thicker on one side than the other. Optically, that wedge acts like a weak prism inside the lens and causes beam deviation. The beam deviation is what we actually measure when we ask for a specification on the lens, and that's if you were to say, look at the path a beam takes through the lens, then rotate the lens by 180 degrees and look at the difference between those two paths, that's twice the decentration. Many times we'll see specifications of a wedge on a lens, and the wedge, of course, would be related to the beam deviation through the refractive index. So while there's a relationship between those two, it's not necessarily one-to-one, and the big difference there is in measurements. The beam deviation is generally a lot easier for us to measure than a wedge. An example of what this might do in an imaging system is given here. This is a multi-element spherical system, and it was looked at in ZMAX using either a very small decentration on two of the lenses in the system of just less than 1 arc minute, or a more typical decentration of the lenses of 6 arc minutes. On the left, you can see the well-standard lens system, the MTF plots there, showing us resolution to above 120 line pairs per millimeter. On the right, you see the decentered version of that lens system, showing a lower resolution in that system, and that shows you the impact of that decentering on the overall performance of the system. Another example of that, not an imaging system this time, but a laser system. If you have a decenter of a lens, as we talked about before, if you rotate it 90 degrees or 180 degrees, you'll see that that path isn't quite the same. You can see that here as we walk through a rotation of the lens system. And so if you were building a laser system where pointing accuracy was very important to you, then well-centered lenses would be very important to make sure that that pointing was repeatable and accurate as it possibly could be. How do we test for centration in a lens? So first we place the lens into a cup and apply pressure to center that lens. And then we secure it by its outer diameter to make sure that the whole system is well constrained. Collimated light is then sent through the lens, and that's rotated around a circle. As the lens rotates, the point of light at focus will also move around a circle, just like you saw in that previous video. And the diameter of that circle is twice the beam deviation. So that's how we actually measure it. Power and irregularity, so these are surface specifications. Power error is either form or sag error corresponding to the incorrect radius being applied to the spherical surface. We can test that by comparing the lens that we manufacture to a reference surface or by using an interferometer. In either one of those cases, any difference between the surface, the ideal spherical surface and the manufactured spherical surface will create an interference pattern, which is also sometimes called Newton's rings. That's due to that difference in either the air gap between the test plate surface and the lens, or to the difference in optical path length between the surface and the test spherical, the transmission sphere and the interferometer. More fringes in this case means a larger error. Each pair of dark and light rings or fringes would correspond to one wavelength of error. Typically that's done at 632.8 nanometers, so that would be the mechanical or geometrical difference between that ideal surface and the one that's been manufactured. There are already some issues to keep in mind when trying to set such specifications. For instance, just like I talked about with wedge and decenter, the difference between, say, a power error and a radius error is not necessarily simple. You can see here from this equation, if you were to look at power error in waves, as you either increase the diameter or decrease the surface radius, the same radius error will cause an increase in the power error. So that means that lenses with either very large diameters or very tight radii will often require a larger tolerance on the power error compared to the radius. So if you're specifying one or the other, it's important to keep that in mind. Typically we see those specifications again in terms of power, but radius is also something we can work with. Irregularity is another surface error. In this case, we look at any deviation between the surface of the lens and that ideal sphere, but then we remove the power error, and anything that remains after that removal is what's known as irregularity. It can usually be obtained by the same measurement as the power. You might use software to subtract the power from the overall surface, or you might use optical tricks such as changing the space between the transmission sphere of the interferometer and the test surface. But in either case, you would remove that power and then look at whatever's left over. One of the issues that can come up is that when you have a lot of power error in a surface, trying to find very small amounts of irregularity underneath those power fringes can be very difficult. So typically we ask that lenses are specified with a 5-to-1 ratio of power to irregularity to make sure that that irregularity is something that we can measure accurately. Of course, there are costs associated with all these specifications, and we'll start with power. So you can see here a relationship between the power error and the relative cost for a particular lens. This is normalized to the lowest cost, so largest power error lens. Obviously, as I said before, there are more complicating issues such as the size and radius and so forth, but this gives you a general trend. And as you might expect, as the tolerance becomes tighter and tighter, the cost goes up. It's not too bad in this example where our tightest specification of a half a wave of surface power is only about 1.5 to 2 times the cost of our lowest specification. However, if we look at irregularity, there's a bit of a different trend here. So it is, of course, increasing as the specification becomes tighter, but this is a much steeper relationship between the two, increasing to 3 to 4 times as much at a 10th wave of irregularity as it is at 1 wave. These are, again, at that 5-to-1 ratio that I mentioned, and it's also important to mention that these costs, relative costs, are multiplicative. They kind of multiply onto each other. So if you were going to specify a very tight irregularity, you would also have to specify a very tight power tolerance, and those two relative costs would be multiplied. Surface quality is a little bit different than these geometrical issues, and it's a little bit complicated, so I'll take a few minutes to explain. Surface quality is generally used to describe defects such as scratches, pits, or digs. Sometimes they can be purely cosmetic, and you just want to make sure that your product looks good. Other times they might cause a small loss in transmission due to increased scattered light. It'll have a similar impact to the overall performance of your system that surface roughness would have. But there are times that are going to be a little more important to you to make sure that the surface quality is high. One of those is if these defects might be located near an image plane within the optical system. In that case, they would be essentially in focus, and so they would be very visible to the user or to the imager or what have you. And those would be times when you'd be much more critical about the surface quality of the optic. Another time is in high-power laser applications. Defects often lead to the presence of optical damage when they're exposed to very high fluences in laser applications. And so that's another time that you might want to specify a much tighter tolerance or much higher quality on your surface. Surface roughness is also generally more important in these laser applications than it is in an imaging application. So that's something to keep in mind as well. There's two standards that we use when we talk about surface quality. The first of those is the mil spec, the PRF 13830B. That's based on calibrated standards and a visual comparison between those standards and the optic that you're testing. That visual inspection, of course, is largely subjective. It's dependent on illumination, the index of the optic, and so forth. But it's widely used because it's relatively inexpensive. The ISO 10110, the latest revision of that is 7. That's, in many people's estimation, more functional than the mil spec because it's based on an actual scratch size or dig size, and it's less dependent on illumination because of that. However, the downside of that is that it's more time-consuming to measure and therefore more expensive. So typically we see things specified on the mil spec. How do we test for these? The dig diameter is the diameter of the largest dig, or alternately that might be an inclusion under the surface. It's given in 1/100th of a millimeter, so that's the dig number. The scratch number is, in ISO terms, related to the width of the largest allowable scratch. There's also limits within that spec on how long those scratches can be. That gets to be a pretty complicated discussion, so probably not to dive too much into those details, but again, that's a geometrical specification. In comparison, the mil scratch number is subjective. We compare to a reference material that's been scratched in known ways and look at the relative visibility or brightness of those scratches. There's, of course, many standards available for that. We sell some of those scratch dig standards through our own website, and if you want to take a look at those and see how they might be applicable to your own optics, we'd encourage you to go ahead and get those and have a look. In future revision of the ISO, which is currently going around and should be out in the next year or two, there will be an additional option for an inspection-based scratch measurement similar to the mil spec, but in there it will be a requirement that you specify which scratch dig standard you're going to use, because they're not all the same. Those are made by different techniques, and there's some variability. The nice thing here is that unfortunately the mil spec scratch standard is no longer made. It was made back in the 40s and doesn't really exist anymore. So there can be a little bit of variability depending on who uses what standards in-house versus the manufacturing standards that are used. Since they're not all exactly the same, there can be some disagreement there on just how visible a scratch is. So by putting that into the standard, it helps you to make sure that you get what you expect to get. Again, as we saw before, we can expect a cost trade-off between the surface quality and the cost. In this case, we list scratch dig. So scratch is the first number, dig is the second, from 10.5, which might be considered a laser quality optic, all the way down to our commercial grade of 8050. And just as you saw before in Irregularity, there's about a 3 or 4 times ratio between the cost of our best surface quality and the lowest, and that has to do with things like yield. You don't always get every lens out at 10.5, so there's going to be yield implications and therefore cost implications. And it's important to be aware that these different specifications actually work together, and you can't necessarily specify them however you want. So first, we'll look at 3 sets of specifications that you might want to choose from. The first is our commercial on the left, in the middle is our precision, and our high precision on the right. The commercial and precision specifications come as a group. So if you order a commercial lens, you'll have all those specs. If you order a precision lens, you'll have all those specs at once. However, on the high precision, those are what's available, but they're not always available in every particular case. It depends on what the other specifications might be. And so I'll walk you through an example of that to hopefully make it a little more clear why that is. So let's start with a low tolerance lens that's going to have some amount of power or irregularity error and a centration error, and those need correction. To fix either power or irregularity, you would have to continue polishing this lens, adjusting the parameters of that polishing process to fix those errors. That, of course, requires you to remove some of the material, and that reduces the center thickness of the lens. If you know that you're ahead of time manufacturing a very tight tolerance lens, you can add material in to give you some more leeway to work with, but you can't do that with infinite precision. So a tighter tolerance on power or irregularity generally means a slightly looser tolerance on the center thickness. The same is true for centration and outer diameter. So we mentioned that the error of centration is a problem with the outer diameter not being at the same center as the surface. So to fix that, you remove more material from one side of the outer diameter than the other. Of course, that reduces the overall outer diameter of the lens, and it also can have small impacts, again, to the center thickness. So that also has limitations in terms of how much you can remove and how precisely you can do that. So generally speaking, the tighter the irregularity or power, or the tighter the centration, the looser the center thickness or the outer diameter specifications need to be, within reason. You can't always do this, just any way you want to do it. It depends on things like we mentioned before, the surface curvatures and the overall diameter of the lens and so forth. And it's important for you to know which specifications in your particular application matter most, and that really comes from the optical design. Of course, that's a complicated process, so I'd encourage everyone to remember that EO is here to help. If you have any questions on how to optimally set the specifications on your design, I'd encourage you to pick up the phone and talk to some of our experts. So running back through the overall specifications. So again, you can see commercial, precision, and high precision. Those will have to be taken on a case-by-case basis, but that's what is achievable typically with our finishing processes. The key takeaways that I'd like you to leave today with this from this webinar: you need to understand the sensitivities of your system so you can avoid over-specifying tolerances in your optics. Over-specifying leads to increased cost and possibly also to increased lead time, so it's important to keep these things in mind. Be cautious when you're specifying high precision tolerances. Yes, we can achieve them, but not in every case or every combination. And to make sure you keep us in mind and talk to us if you have any questions on how to do that. And with that, I think we've got a little bit of time to take some questions that have been posed, so I'll turn it back over to our announcer.
Thank you, Nathan. Yeah, we answered many of your questions during the webinar, some great questions, and there were a few common and notable ones that came up that I think are worth sharing. So the first one that we seem to get a lot of is, what surface quality is required for laser optics applications?
So as I mentioned during the talk, in laser applications, there's usually a greater focus on surface quality, both for scattered light and also for damage. So typically, you might expect a recommended surface quality of 2010 or even possibly 10.5 if you've got high laser powers.
Thank you. Another question we heard a lot was, what is the impact of a large clear aperture size on the cost?
So the trick here is it's an artifact from the manufacturing process called edge rolls. So as you get very close to the edge of the optic, the curvature can change, become a little steeper. And so you typically want to stay a certain distance in from the edge in order to avoid that edge roll. So in a very tight irregularity, such as 1/10 or 1/20th of a wave, smaller clear aperture than 90%, maybe 85 would be important to make sure, or greater than 1 millimeter from the edge would be important to make sure that you're avoiding that edge roll effect.
Perfect, thanks. And finally, are there other important types of tolerances that I should pay attention to? Received that quite a number of times.
Yes, so as I mentioned today, one of the ones that often interplays with the ones we talked about today is diameter and center thickness. So our diameter tolerances are all given with an upper tolerance of +0. For the the negative tolerance, it's given as minus 0.1 millimeters for normal, 0.05 millimeters for precision, and 0.01 millimeters for high precision. Center thickness was the other one that's really important. Typical tolerances for center thickness are plus or minus 0.2 millimeters for normal, plus or minus 0.05 millimeters for precision, and plus or minus 0.01 millimeters for high precision.
Great, thanks, Nathan. That covers it. And thank you, everyone. We appreciate you being there. And just a reminder, A link to today's recording will be sent to all participants shortly. And for more information on our manufacturing capabilities, please visit www.edmundoptics.com/capabilities. You can also reach us via email, the Edmund Optics 1-800 number, or through the live chat feature on the website. So thanks again for joining us today. Thank you, Nathan, and we look forward to seeing you next time.